Alright, example 14.2, page 322. We have an hydraulic circuit. We are given the length of all the pipes and what type and how those pipes are connected. We are given the flow rate. We are asked to calculate the pressure at the entrance point. So what we do, we fix in point 1 and point 2. So point 1 and point 2 at the exit. Now, first thing first, let's calculate the Reynolds number. To calculate the Reynolds number, we need to know what fluid we have, and that's water. So we know the density, we know the viscosity. The velocity, it can be taken from the flow rate that is given. So this is the velocity at point 1. That's gonna be also the velocity that you're gonna have throughout the pipes, because the pipes, they all have the same diameter. So the Reynolds numbers is gonna be 45,000. 45,000, that tells me that is a turbulent flow. So now let's apply the Bernoulli, the mechanical energy equation between point 1 and point 2. So of course there are no turbine or pump, so we're now considering them. We just have the losses, Z due to losses. So what kind of losses we are considering? Let's consider first the major losses. Before you do realize that here at point 2 we are outside, so that's gonna go away, and so what we are left over here is with this equation. Head losses, as I was saying, the head losses, they are in this particular, we consider first the major losses. Major losses are a function of the friction factor. So we need to find the friction factor. The pipe is actually drawn tubing. So by looking at table 14.1, drawn tubing, it tells us that the equivalent roughness is 0.00005. We know what's the diameter, so equivalent roughness divides the diameter of the pipe. Diameter of pipe is over here, 0.75 inches. It's gonna give us 8 multiplied 10 to the 5th. We know the Reynolds number we calculated before is 45,000, so we roll to the Moody chart. So it is actually about a bit lower than that. There. 45,000, it's about over here, so if we follow in that line, it's flattening out about here, so it comes to about here. That point, when we're reading it, it's gonna be about 2.15, 0.0215. We have our F. What we need to be able to calculate is what is the velocity of point 2, and again the velocity of point 2 is just gonna be your Q over R2. So velocity of point 2, V2, there is Q over A2. plugging in all the numbers that we have. L is the total length of the piping. We are coming up with our pressure. Now, that is if we were considering only the major losses. If we are considering minor losses, we're adding also this term. This term, we need to be able to calculate what is it, K, the K. So there is KL, 1.5 for each elbow, plus 10 for the wide open globe valve, and 2 for the wide open valve. You sum all of those numbers, and you are then getting it 10 plus 4 multiplied 1.5 plus 2, so that's 12 plus 6, 18. Okay, I want to point out that those coefficients, the 1.5, they were those elbows, they were coming from table 14.2, whereas the coefficient for the valves, they were coming from over here. So what you're using is table 14.2. So that gives us an extra 9.17 psi. So the total pressure drop, it will be the 21.3 psi plus the 9.17 psi, and that is 30.5 psi. Notice in this particular case that losses, the major losses and the minor losses, are contributing on the same order of magnitude. I mean, yes, the minor losses are actually a little bit less than the others, but not that much less. In the following example, instead, that works exactly the same way, but we really see here how the major losses, they become really major when we have very long piping system. In this particular case, we have the Alaskan pipeline that is long 800 miles. So same equation, start at the beginning, and the major losses are in function of this. We know that is a steel piping, so we know what's the Reynolds number, so we are going to look again at the friction factor, and we coming up to calculate the losses are actually pretty huge. In this particular case, we really don't need to calculate any minor losses, because this number is so huge in respect to the other that it won't matter really the geometrical shape on which the pipeline is. Moving on to example 14.6. Well, this is just really an application to show you how to calculate the boundary layer thickness transition using the equation that I showed you on the PowerPoint, that are this equation, and we calculate when we transitioning by using that equation. Those two equations, they are represented here and they are represented here. Just a matter of substituting the proper values, and you can easily go through the example and calculate what would be your boundary according to different type of fluids. So let's move on to another example. Example 14.7. What we have is a 4 feet by 8 feet piece of plywood that's fastened to the roof of a car that is driven at 55 miles per hour. So we want to calculate what's the drag caused by shear stress. So what does it mean in the direction of the movement of the fluid? So which equation we're using, of course, is gonna be the CD. Is a drag, is not a lift, is this drag over here, So that equation we need to calculate the drag. We want to calculate that, the drag, so we need to find what's my CD. So how do we work that out? See, here is the equation. And how do we find CD? Well, we need to know what is it, the surface roughness of the plywood. And again, we're looking at the table 14.1, saying table that we had table 14.1, the one where we had the roughness. Where is the plywood? Wood. Okay, so what we have, we are coming up with an intermediate number over there, and so we're coming up with this number over there, divided by what we need to know is E over length, epsilon over length. The area here is represented, of course, by the length and the width of your plywood, so your 4x8. To find CD, we use in figure 14.4 that's up here, and so we are able to calculate our E over L. 8 is the length, so this is the number that we're looking for, the Reynolds number over there. We have all the elements to find it because we are considering that's density of air, and we can look it up at the end of the book, what's the normal density of the air. And so we are just calculating the Reynolds number. We know. So by looking at this 4.11 10 to the 6 and 3.75 10 to the minus 4, we say 3.75, 3.75, so it's gonna be a line that's pretty much runs like this, and we are meeting the Reynolds number at 10 to the 6 for 10 to the 6, so about there, so we are rolling about there. So my CD, it is calculated around that number over there. I'm not very impressed with that. Oh, I made a mistake there. Alright, so what we have is our Reynolds number. Okay, so what we have is our Reynolds number is 4.11 10 to the minus 6 and 3.75 10 to the minus 4 is A over D. 3.75 times minus 4 is gonna be a number between this and that, so this 2 and this is 5. It's gonna go about like that, something like that. 4 to the 10 minus 6, so 4 to 10 to the 6 is gonna be about like that, so I'm gonna meet about, like that, the point it will be about there. So the book estimates that at 0.066. Okay, now that we have CD, we know what is the velocity, we know what's the area, we know our CD, and that's the density of the air. So that is the drag that you do have. Final example. the drag of an automobile. This is a straight application of this equation. We are given pretty much everything. What I want to point out is that A is the front cross-sectional area, so it is practically your height multiply the depth that you would have for the car, so your cross-sectional area over there. So in this problem you want to calculate what was the drag force. Well, let's want to know the power, so to know the power we need to know the drag force for a car that's running at 65 miles per hour between a model of the 40s and a models on the 1000s. Well, by looking at the number over here, we notice right away that of course the coefficient of drag of this car is way higher than the coefficient of car of a more modern car. That of course, what does that mean? It means that it's more aerodynamic. But also what we notice is that this car is taller than the other. See, it's taller. 5.1 versus 4.3. The width is the same, but it's taller. So what does this mean? It means also that the area will be higher. So area will be higher, the CD will be higher, so of course you can expect that the drag force on the whole car will be way higher, and that's what you actually getting. The drag for a car on the 40 is 158 pound, whereas for the 2003 model is 72.5 pound. If you want to know what's the power, of course it's just a question. Power is just velocity multiply force, so the velocity of the car multiply the drag force. The power to overcome is 27.4 HP versus 12.16 HP. And yes, these are all the examples I wanted to go through for this chapter.